Okay, so thanks. So thanks for the introduction. So basically, I wish to thank the organizers and in particular Rama for giving me this nice occasion to participate to this meeting and to present some work. So basically, so these things is a work in real progress. So I mean, it's so I hope that I will get some input from you to be able to ameliorate a bit the ideas I'm trying to develop. And basically, it's related somehow to some. So there is a connection with Srinivasan. So basically, I think that the ideas behind these things were initiated a long time ago, so almost 20 years, while I was visiting Yale, where you were still there. And I spent 2 weeks in Yale, and I shared the office with Greg Eyink. And it was the first time I was meeting Eyink. And we had a lot of discussions about spontaneous stochasticity and things like that. And basically, all these, this was very important input for the things I will tell you. So basically, I want to also to acknowledge a kind of indirect contribution from Srini. So basically, the idea, so this is work which is done in collaboration with Simon Talabarc, who is here, who is presenting a poster also, and it's about a different way to think about of inviscid flows and turbulent flows, and in particular Euler equation with irreversible dynamics in terms of Lagrangian maps of the way the fluid elements are moving inside the flow. So basically, I will try to start with a very mathematical slide. So it will not be the last one. And so basically, it's just to state what could be the relationship between inviscid flows and turbulence. So we all know that if we look at what's happening inside the inertial range, if we are sufficiently far from forcing and dissipation, the dynamics could be more or less described by something where pressure, time derivative of velocity and nonlinear terms are important. So in principle, something which looks like Euler equation. But we are doing some kind of coarse-graining of that. So it's not clear what's happening. So from a more specific formulation of what we intend by the turbulent problem, and in particular the stationary turbulent problem from a mathematical viewpoint. So consider that we have the Navier-Stokes equation, okay, so with some input of energy, so some random forcing, for instance. And now, so as it's a random forcing, basically, I'm able to do some average with respect to this forcing of any quantity which is connected to the velocity field, structure functions, spectra, etc. And now, if I'm taking a sufficient long times, so I'm supposed to be in a stationary regime, so where basically I have forgotten the initial conditions. And then this measure, which is the average with respect to the random forcing realization, will become independent of time. So it will be a statistically stationary turbulence. And now, but so the idea, so basically we call it usually the turbulent measure. Okay? So it's the measure of the flow. And now the idea is to, once we have taken this limit of infinite time, we want to take the limit of vanishing viscosity or infinite Reynolds number in order to understand if there is some limit of which will be turbulent in that case. Basically, and this will be the final object that we want to characterize. So something which is a probability measure on velocity fields, which has been obtained by taking infinite time of a given flow, and then limit of vanishing viscosity. And the problem is that these two limits, time to infinity and viscosity to zero, are not necessarily commuting. So it's the case in Burger's equation, and this is simplifying a lot the discussion for Burger's equation, but for Navier-Stokes, there is no clue that this will be the case. Still, one can be tempted to interpret this turbulent measure, so this turbulent ensemble of velocities, as some kind of solutions to the Euler equation. So which will be like assuming that the two limits are commuting. So it's clear from, it's far from clear, but I mean, this is motivating a lot of work, in particular by people doing mathematics, on trying to construct some weird solution to the Euler equation, which will be able to describe turbulent flows. Okay, so one question that we can ask is, if we take large but finite Reynolds number, is there a signature of an Euler dynamics, okay, in the developed turbulent regime that we observe, so that basically it will be a kind of partial commutation between these two limits. Sorry. What, the large? Yes, this one? Yes, it's the same. It's analogous to the question I asked on the first slide. Yes, more or less. Yes, it's the same kind of question. Yes, it's the same question. This is the main question I want to address. So now, basically, to continue a bit on the mathematical side, so there have been a lot of work, I mean, since the early 90s, on trying to and even before, on trying to make a link between constructing Roth solutions to the Euler equation and turbulence. I mean, this dates back from what is called Onsager conjecture, which was stating that even if you take a solution of the Euler equation, so with no viscosity, and you make it Roth, so you allow that the gradients are not defined, for instance, then this solution is not conserving any more energy, and in particular, it's dissipating energy if the Rothness is sufficient. So this is basically Onsager's conjecture. And this is linked to what is called in the physicist jargon the anomalous dissipation of energy in the limit of infinite Reynolds number. The fact that you still have a finite dissipation of energy even if you make the Reynolds infinite. So so what was shown by mathematicians is that typically such solutions that you make Roth are not unique. I mean, it's very hard for them to understand how one can recover uniqueness of these solutions, which means that you have a bunch of solutions which are very weird. So basically, the Schneerman, for instance, has constructed solutions of Euler equation, so which are Roth, which starts at minus infinity with a zero energy, so the velocity is zero everywhere. At some time, arbitrary time, you blow energy, so you create a flow, and then this flow disappears, and you have nothing at time plus infinity. So I mean, this is completely unphysical. I don't know if you agree. And so basically, which means that since you have the existence of such solutions, I mean, you can construct any solution. So more recently, that there was a different way to look at the problem, saying that if we want to be closer to physics, what we need is to make this solution admissible. So for instance, this solution should not create energy, they should only dissipate. And even this criterion is not enough to show uniqueness. And in particular, for instance, if you take admissible weak solutions and you look at an initial velocity, an arbitrary initial velocity with a finite energy, then almost all this initial velocity will lead to an infinite number of solutions to the Euler equation, which means that, I mean, it's very hard to talk about dissipative solution to the Euler equation. Mark, you look like having a question. No, okay, I'm sorry. Okay, so basically the main message is that there is not really straightforward way to ensure unicity. And again, what we can ask is whether some turbulent data, so some analysis of turbulent data, can give some more constraints on the way one is constructing these specific solutions, so these weak solutions to the Euler equation. Yes, basically that's what I was meaning by providing further constraints. But of course, all these things is in the framework where one is assuming that maybe one can do some kind of commutation between infinite Reynolds number and stationary regime. Let me continue. So now there is another effect which is pretty important, and which is what is called spontaneous stochasticity. So basically, most of you, so we didn't talk much about Lagrangian turbulence, but most of you know that at very large Reynolds number, I mean, if I take two particles and I look how they separate in the flow, since the velocity difference is typically like their distance to the power 1/3, these particles the distance between these two particles will grow like a power law, like roughly like t to the 3/2. And this will be independent on their initial separation, which means that in the limit of a very large Reynolds number, one can take, in principle, two particles arbitrarily close, and they will automatically separate completely. Okay? So which means that basically there is a very weird behavior of the Lagrangian flow. So typically, one can understand this kind of phenomenology by looking at a very simple model. So one is considering a stochastic differential equation, so a Langevin equation, where I'm assuming that there are two terms, so in time in the increment of some variable r, it's 1D. One which is a drift, which is proportional to a power law of r. Okay, so like something like r to some power 1/3. But I'm putting some smoothing here, just to be sure that I don't have a singularity at r equal to 0. This is a parameter, a kind of ultraviolet cutoff, which is smoothing things at r equal to 0. And then I'm adding also a noise to that, a diffusion. Okay? And what's happening is that, so you see that if you do abruptly, so and you start with an initial condition which is itself at 0. So if you put this to 0 and then eta to 0, I mean your equation will be dr dt is equal to r to the 1/3, and you know that the solution is r equal to 0. R is staying 0 at every time. But now, if you take the limit in the inverse order, which means that first you make the ultraviolet cutoff to 0 and then the diffusion to 0, then the limit is very different. Instead of having a single solution at 0, you have a full distribution of solutions, which is obtained in the limit, even if you are taking the cutoff, both the cutoff and the diffusion to 0. And basically, this is what is called either the explosive behavior of Lagrangian tracers or the spontaneous stochasticity of tracers. And this was rigorously shown in model flows like Kragnan random flows, but has been just observed pretty weakly in real turbulent flow. But there is no doubt that it's taking place. So which means that, so the conclusion of that is somehow is that the Lagrangian flow itself, so the Lagrangian flow which is the application which is associating to a given initial position in the flow, the position of the fluid elements after a given time t. Okay? So this Lagrangian flow cannot be really considered as an application, because if 2 points can be mapped to 2 different places, I mean, it's not a map. Okay? So it's not an application, a usual application. And then the message somehow is that one needs to understand this kind of transport with a probabilistic description. And this is known since the work of Bernard and Eyink, and this is mainly the discussion I had to acknowledge with Eyink about these things. And the question now is that, okay, so if this is happening in large Reynolds number turbulence, I mean, how to understand the term which is associated to turbulent advection? So in the Navier-Stokes equation, I mean, you have a material derivative, which means that you're looking at the evolution of velocity along a fluid element somehow, and the velocity along a fluid element is transported by itself, and then is accelerated or not by the pressure gradient. But now, if you cannot think about this flow as just an application, but you have to think it in terms of probabilistic viewpoints, I mean, why can we think about the turbulent solution just in terms of a usual PDE? I mean, why don't we have to put this kind of probabilistic vision? And actually, the situation is even worse, because the spontaneous stochasticity is not valid only for these Lagrangian tracers, but even for solutions to the Euler equation themselves. So let me explain you. So basically, because of the fact that this advection is ill-defined and has to be thought in terms of a probabilistic motion, basically, there are some situations where you introduce a singularity in the flow. So for instance, you take Kelvin-Helmholtz, where you assume that you have a discontinuity in velocity. So this part here above is going to the left, and this part here is going to the right. So what is shown as a black line is somehow the vortex sheet, which is separating these two pieces. And now, basically, because the flow, the Lagrangian flow is ill-defined, the transport of this line by the flow itself is ill-defined because it's rough. Basically, it's very hard to understand to what position a given point here will be mapped. And again, one has to think in terms of a probabilistic approach. And since the flow is constant everywhere and the vorticity is concentrated on this line, basically, one has to understand the transport of vorticity by the flow in terms of, again, a probabilistic approach. And this, so you can see it in the following way. So in order to describe these things, so one way to do it is to use what is called the Birkhoff-Roth equation. So the Birkhoff-Roth you're doing the following thing. So it's 2D, so you look at this 2D system, and then you write the position, so x and y positions of your line in terms of a complex variable. So you complexify the 2D plane. And now, if you write the Euler equation for that, basically it's becoming this equation. So it's a kind. So somehow, what you do is that you're applying the Biot-Savart formula. So you express the velocity in terms of the vorticity with this integral formula, and basically you apply it on the line itself. It's a closed equation for this z, which is the position here. So again, one has to do two smoothing. So one smoothing, which is correspond to smoothing this integral, because this integral is ill-defined at s equal to s prime. And the second one, which is to add some noise. So you put some noise for the value of the vorticity on the line, and you make, again, the following thing. So you first make this cutoff to 0, and then the noise to 0, and then you get a real finite size solution. Yeah. I can show. I need to click to show the movie. So basically, this is what's happening. So you have a random, so for a finite value of epsilon and of the regularization, you have a random spreading of this vortex sheet. And now, if you make the both things to 0 in the proper order, I mean, you will still observe this kind of spreading, and this you can see it from this picture. So basically, which is representing the variance of the spreading in the y direction as a function of time for different values of epsilon. And what you see is that when you decrease epsilon, I mean, things are converging to some stuff which has a finite explosion. Okay? So what does it mean? It means that this kind of flow is much more unstable than anything that is usually chaotic in the following sense. So if you take a flow, you say it's chaotic, what it means that if you have a perturbation, this perturbation will grow exponentially with time. And so the perturbation will grow exponentially, and by linearizing your system, the size of your perturbation will be proportional to the initial size of what to put. Okay? And so, in principle, if you make this initial size to 0, the finite time perturbation instability will have also a size going to 0. In that case, what we have is that the instability is having a finite size, whatever is the size of the initial perturbation. Okay, so which means that it's something which is much more violent than anything chaotic, much more unstable. So now again, I mean, these kind of considerations are advocating for a probabilistic description of the velocity field. So let me just summarize a bit these 3 points. So what I was telling you is that there are problems in defining the unicity of weak solutions. Mathematicians have real troubles. So weak means the non-differentiable rough solutions to Euler equation. The tracers themselves have an explosive separation which might be incompatible with the usual way we understand advection. And the velocity can itself be spontaneously stochastic and have these finite size probabilistic perturbations and instabilities. So which means that somehow a position here has to be mapped to different positions. So, or in other terms, the velocity has to be thought in terms of a distribution of velocities at a given point in space and time. And this has been formalized by mathematicians, so in particular by Diperna and Maeda, who are talking about distributional solutions to the Euler equation. And they were able to show that, so if one is weakening a lot the definition of the Euler equation, I mean the definition of the solutions, and think in terms of this probability distribution, they were able to show that in the limit when one is taking vanishing viscosity, there is a limit which corresponds to a solution which is described in this sense, in this very weak sense. Okay? And the question is it relevant for turbulence? And how, again, to detect this from data? So how to construct this solution? So let me maybe formulate more pragmatically what we mean. So assume that I have a flow, viscous, but I want to detect from it an Euler dynamics which will be describing what's happening in the inertial range. So what I do is that I'm cutting it, I'm doing some coarse-graining, okay, and I cut it in small boxes. And in all of these boxes, I'm looking at the map, which is sending one box to another box at another time. Okay? So since I want the flow to be incompressible, I mean, so I have maps from box to boxes. I mean, at the end, what I'm doing is just a permutation of all these boxes. Because, I mean, mass is conserved, the flow is incompressible. So now, the thing is that since these permutations are not uniquely defined, because I want to have a probabilistic approach, then what I need to think about is a probability, okay, of having a permutation from time n to n plus 1, sending the box I to the box j. Okay? And if I want to look at the probability on all these permutations, this is what is called the doubly stochastic matrix. So it's a matrix which is telling me, so the ij, the I column j line is telling me what's the probability of having I mapped to j, and as it's a probability, it's doubly stochastic, and as it's a probability on permutation is doubly stochastic, which means both the lines and the columns are summing to 1. So it's a very specific matrix. And the question is, can we understand an Euler dynamics described this way in terms of these probability on the permutations? And the answer is yes, thanks to what is called generalized Euler flow, and which was developed by Jan Brognier in the late 80s. So let me first. So basically, this Brognier formulation is based on the variational principle. So the variational principle is a kind of generalization of what has been known for a long time for Euler dynamics, which is Arnold's Lagrangian variational principle, which is stating the following thing: is that if one is looking at a regular solution to the Euler equation, then this regular solution can be understood as is minimizing a given kinetic energy. So basically, what one has to do is that the real map from time 0 to time t is given by minimizing over all applications, all maps, the kinetic energy along this map. So somehow, in other terms, if you want all the solution, the smooth solutions to Euler equation can be defined as geodesics on the space of volume-preserving differentiable maps. So basically, somehow, Euler is such that you're doing a motion which is minimizing kinetic energy and incompressible and smooth. And so any motion which is minimizing kinetic energy, which is preserving volumes, and which is smooth, is described by Euler equation. So now, how to generalize this thing? So what Brognier proposed is to say, okay, instead of thinking about smooth maps, I will think about probabilities on the space of maps. Okay, so he's weakening all the notions. So first, he's weakening the fact that the map is incompressible. So he's just saying, in average, my maps should lead to something incompressible. he's saying instead of having each time something mapped to somewhere, again, I want it in average. So I'm fixing the final condition. So I start from a given configuration of the flow. I'm fixing the final condition, and I want in average this final condition to be satisfied. And then he's generalizing the action again by saying, in average, I'm defining the kinetic energy of all these maps. And what's happening is that even if the solution is that weak, that generalized, what can be shown is that solutions are existing, okay, which is important. I mean, that it's not something which is meaningless. That for final maps which are given by a classical solution of the Euler equation, which means a smooth solution, but then even if you are asking stuff very weakly this way, you are really capturing this smooth solution. And the most important thing for us is that if one is considering deep Anamaida solutions, so these solutions which are distribution of velocities at each point of space and time, then they can be described by this variational principle. Okay. So the question is, can we make this relevant for turbulent Lagrangian maps? And so for that, what we have done is that we have done numerics where we are trying to construct this minimal probability distribution over maps, which are minimizing the action in average. And for that, what we are doing is that we are using, basically we are introducing the Gibbs measure associated to the action which has to be minimized. And we are doing some Monte Carlo stupid Monte Carlo simulation in the sense that, so basically what we have, let me try to be more concrete. So we start from time 0 and we want to construct the flow which is mapping this distribution of matter to a prescribed distribution of matter at the final time. This is our data. We don't know anything about velocities. And now what we do is that basically we divide our time in different time intervals, and basically for each jump between different time intervals, we are computing the cost in kinetic energy. And what we do is that we want to construct the proper sequence of maps like that, which is minimizing the kinetic energy. And for that, what we do is that we are introducing some temperature. So this 1 over beta in this thing. And in principle, we have to make this temperature to 0 to be sure that we have the minimum. And now we do for a finite temperature, we are doing a Metropolis Monte Carlo thing, which means that somehow we let things fluctuate and accept or not random change with a cost which is given by our action. So now basically, so now if we do that, let's try a test case. So before going to turbulence, let's try a simple case, which is a stationary solution to the Euler equation, given by what is called the Beltrami flow, or if you prefer, a cellular flow. So somehow it's 2D. So basically there is no linear interactions between the different modes. And in principle, you see, as you see from the movie, the matter is I mean, there is a big eddy, and the matter is flowing along this eddy. So that basically what I'm showing here is a way to represent the map after a given time. So now, if one is indeed applying our system, so basically what we do is that, so we fix a final condition, or the map. Basically, these are the non-solution that we can compute explicitly. And by looking at different values of the inverse temperature and decreasing the temperature, so this is, beta is 1 over the temperature, so we increase beta, so which means that we decrease the temperature, you see that we are moving to reproduce the exact solution without any knowledge about the velocity field. And so now, if we try to do that for a final time which is too large, things are not working anymore. So actually, this solution is working only for a fixed final time. And then what's happening is that somehow you see that if we take some final time, so if we impose the map at a final time which is too large, where the flow has turned too much, basically the classical solution is turning like that, while this generalized flow is doing something which doesn't look really physical. And so this can be understood. So there is a way to understand this maximal finite time that we can prescribe, and basically with a hand-waving argument, it's doing like this. So assume that we have just a solid rotation somewhere. So if we are before the finite time, it means that we are prescribing, for instance, this particle to be arrived at this time after time t. Okay? So, and basically, there is only one way to do it, is to take this kind, so the flow is being incompressible, is to take this path and to bring it here, which is the real flow that we want to show. So now, if we are above T star, it means that we are asking the matter to do something which is more than half this term. So which means that in that case, if we want to minimize kinetic energy, it's much better to go the other way. Okay? And so basically, for this local thing, the T star will be here. But now, since it's not solid rotation, but we have different rotation rates, so basically, in the case of the Beltrami flow, I mean, we get a mess in the middle, but it's not a pure mess. I mean, you see that actually the particles are doing some kind of deterministic motion, but which seems to us completely physically irrelevant. So now, so basically, if we look at we can reconstruct the energy spectrum between these two times, and what we see is that if we have times less than this critical time, when we have something which looks like what we expect, and of course with some thermalization at small scales, which corresponds to the fact that we have a finite temperature, so we have this beta which is finite. But as soon as we are increasing above this critical time, basically we have large-scale modifications, which means that indeed it's not like if we were just adding some noise to the trajectory, but we are changing the large scale. So we have to get rid of these things. Maybe I will drop all that. So now let's try to do a first move toward turbulence. So what I'm considering now is applying this kind of method to the direct cascade of entropy. So why do I want to do that? Is that if I'm assuming Euler dynamics, I want to minimize the kinetic energy. So basically, this thing, I mean, I'm not introducing any irreversibility by hand in my system. The action is, yes, the action is time reversible. And so basically, there is no way that I can obtain something which will resemble an irreversible solution to a turbulent flow. So what I'm doing is that I'm considering a very specific case, which is a two-dimensional direct cascade, where in principle, the kinetic energy is almost conserved because it's rather flowing to the large case, so at least in a given regime of the decay, while entropy itself, which is cascading toward the small scale, is dissipated very quickly. So the general question I want to address is that can we reproduce these behaviors which of conservation and cascade towards small scales? Can we detect what is the maximal time to which we have to discretize in our system? And then is the information on irreversibility contained somewhere in my problem? Not in the variational principle, but maybe in the final conditions I'm imposing. So basically, if I look at the different regimes of 2D turbulent decay, so basically the blue line is energy, the red line is entropy, so there are two regimes. So a first one where there is a short and the sharp decrease of entropy, while energy is almost remaining the same, and then followed by a very slow exponential decay, where entropy is order of magnitudes below its initial value. And if you look at snapshot, so in this regime, you have what is usually known as a 2D turbulent flow, while in the long-term regime, I mean, you have something which looks a lot like a Beltrami flow, where you have no linear interaction, so no creation no dissipation of entropy. So now I'm applying the map, and I'm trying to construct a vorticity on this map. And the vorticity is obtained by a simple differential. I mean, I have coarse-grained my space, so I'm just taking finite differences. I'm constructing a vorticity. And what you see is that this is the solution I expect. And once I'm reconstructing the vorticity with this variational principle, what I get is something which is very similar. When you recognize, of course, it's coarse-grained, but you recognize the different structures here, there, the blue things here. But now, if you take a finite time too large, I mean, you don't catch anymore the same structure, and you see that you have a mess appearing in the places where you had these big vortices, which means that you are above the turnover time that is allowed by your variational formulation. And now you apply this to try to reconstruct the decay, and what you see is that, so I mean, in this very sharp regime of decrease of entropy and almost conservation of energy. So the solid lines are the expectation I have, and the dots are what I remeasure by reconstructing the flow. And you see that I'm able to, at least for some time, to reproduce the decay, so to break the irreversibility of my formulation, except that at some point I have some detachment here, and my guess is that this is due to the fact that I have a finite temperature again. So at some point I'm not able anymore to catch exactly the right flow. And to conclude, so basically now, so this is just a summary, but what I want to stress is the possible extension to 3D. So 3D, of course, is much more complicated than 2, much more costly. And the problem also in 3D is that now what I have done here is to think in terms of permutations, but in 3D I want to really think in terms of probability of transition. And so one has to reformulate the variational principle in order to account for that. And the problem is that if now one is dealing with probability on permutations, the problem is that one cannot do a Monte Carlo in a stupid manner because it will cost too much, and even more in 3D. So what we are working on is to try to develop some more effective optimization algorithm to be able to tackle that. And just to finish, just the last thing is that if we find that the data is agreeing with this variational formulation, which means that some coarse-graining can be described by Euler dynamics. So it's a generalized Euler dynamics, which means that basically we have a formulation for the dynamics at inertial range case, and which means that maybe from this formulation we can design new observables or new conserved quantities. And in particular, there is an interesting conserved quantities, which is the circulation, which is directly associated to the variational principle, and which might be conserved in a probability term. And this is in connection with the talk you gave at the APS-DFD about the fact that circulation seems to be a very strong quantity for inertial range dynamics with scale invariant statistics. And I will conclude there.
So let's thank the speaker first. We have time for only one question.
Yeah, probably another way of saying that unphysical thing, seeing it, is that it's going up the pressure gradient. Like it's not got, your random thing doesn't have any information about the pressure till it is.
So the pressure is hidden,
yeah,
in the fact that I'm just looking at incompressible flows, incompressible mapping. I mean,
but the unphysical motion is up the pressure gradient in your large time.
My guess is that more is like something like I'm allowing weird behavior of the pressure. That's something like it's a changing sign in a very abrupt manner, and this is what is separating the smooth places and the random places. Yes.
Would that all be important for the considerations you are talking about? I mean, the turbulent velocity field is rough only in the inertial range. Yes. But then there is a cutoff, and beyond Kolmogorov scale, there is so much more happening, and it makes everything smooth. Somehow, want it.
So basically, what I want to defend, to advocate for, is the fact that so basically I want an inertial range. A description of turbulence. But if I want this inertial range distribution of turbulence, independent of what's happening at small scales, except the fact that indeed the small scale will dissipate energy, basically I cannot think in terms of velocity field in the inertial range. I have to think in terms of transition probability from places to places. And there is, in terms of this transition probability, there is a way to write down Euler equation. This is
Let's thank the speaker once again.